Hi, in this lecture, the analog signal transmission and reception methods are introduced. In particular, the part 1 of the amplitude modulation methods are discussed. The outline of the lecture is given here. After briefly introducing some background required for our analysis, we will discuss what the analog modulation is. Then the two of the amplitude modulations are presented in this part. Namely, these are double sideband suppressed carrier and conventional double sideband amplitude modulations. Let us first have some background which will be helpful for our discussions and analysis. The energy and power content of a signal are important for us to quantify the performance of modulation methods. The energy content of a signal x of t is given here. Then the power content is like that. Based on its power and energy level, a signal can be categorized into energy or power type signal. More clearly, a signal is an energy type signal if its energy is less than infinite. It is a power type signal if its power content is between 0 and infinite, as introduced in the slides. Here, it is important to notice that all periodic signals, except for some signals like x of t equals 0, are power type signals. Actually, in our analysis, we will mostly focus on power type signals. The time average autocorrelation function of the power type signal x of t is here. It is clear to see if the parameter tau is set to be 0, then the autocorrelation function reduces to power content of the signal. By taking the Fourier transform of the autocorrelation function, we can obtain the power spectral density of the signal, which represents the amount of power at various frequencies, and therefore its unit is power per hertz. Transmission of a message signal usually requires a shift of message frequency range to another range, which may be more suitable for transmission. A shift in the frequency range is accomplished by modulation methods. Although the digital modulation mechanisms are frequently used in modern communication systems, analog signal transmission is still widely employed in audio and video broadcast. In this lecture, we focus on the transmission of analog signals by carrier modulation. Let us now introduce the main assumptions we will follow throughout our analysis. Message signal, denoted by m of t, is assumed to be a low-pass signal with the bandwidth W, which means its frequency content ranges from -W to W. Furthermore, the message signal is considered as a power type signal, having Pm of power. Therefore, Pm can be clarified as given in the following expression. For all types of modulation methods, a carrier signal is used to carry the message signal. In our discussion, we will use a carrier signal like this. Here, AC stands for the carrier amplitude, FC is the carrier frequency, and phi c is the phase of the carrier. We consider the transmission of an analog signal by impressing it on either the amplitude or the frequency of a carrier. When the amplitude of the carrier is linearly related to message signal m of t, the result is amplitude modulation. When the phase or its derivative is linearly related to m of t, The result is phase or frequency modulation. They are collectively called as angle modulation. In this lecture, we will focus on the amplitude modulations. As we have just defined, in amplitude modulation, AM for short, the message signal M of t is impressed on the amplitude of the carrier signal. There are several different ways of amplitude modulation. These are double sideband suppressed carrier, conventional double sideband, single sideband, and vestigial sideband amplitude modulations. In the remainder of this lecture, we will investigate these modulation types in the given order. Let us start with the double sideband suppressed carrier amplitude modulation. In this method, the modulated signal is obtained by multiplying the message signal M of t with the carrier signal C of t as follows. Where U of t represents the amplitude modulated signal. Now we can investigate the bandwidth requirement for this modulation method. Actually, we need to take the Fourier transform of the modulated signal U of t. From the Fourier analysis, we know that the multiplication in the time domain equals to the convolution in the frequency domain. Therefore, we can write the following. For the evaluation of this convolution, let us recall some basic Fourier transform pairs. By substituting the Fourier transform pairs, we can obtain the Fourier transform of the modulated signal. The convolution of the M of f with the delta functions is clarified here. Finally, the Fourier transform of the modulated signal is given. The figure shows how the modulation changed the magnitude and phase spectrum of the message signal. The magnitude spectrum of M of t is shifted by the carrier frequency fc. The phase spectrum is translated in frequency with a phase offset phi c. The figure reveals that the bandwidth of the modulated signal UFT is 2W, while the message bandwidth is just W. Therefore, the channel bandwidth required to transmit the modulated signal is 2W. In the spectrum of the modulated signal, the blue region is called as upper sideband, in which the absolute value of the frequency is greater than the carrier frequency fc. The red part is called lower sideband, in which the absolute frequency is less than fc. As you notice, just one of the sidebands contains all the frequencies in the message spectrum. Due to these upper and lower sidebands, the modulated signal is called a double sideband signal. Furthermore, no carrier component is included in the modulated signal. This is why it is called as suppressed carrier. Let us have an example. Suppose that the modulating message signal M of t is. The question is determine the modulated signal and its upper and lower sidebands. By multiplying the message signal with the carrier signal, the modulated signal UFT is obtained. Using the product to sum formula of cosine function, the modulated signal can be finally written. In order to find the spectrum of the modulated signal, the Fourier transform of the cosine terms are first given. Then, based on these transform pairs, the spectrum of the message signal is expressed. Finally, the lower and upper sidebands of the modulated signal are identified. After determining the bandwidth requirement, let us now focus on the power content of the modulated signal. Without loss of generality, the phase of the carrier is assumed to be zero, since the power is independent of the phase. The time average autocorrelation function for the modulated signal is here. By using the product to sum formula of the cosine function, the autocorrelation function is re-expressed. The autocorrelation function is detailed here. There are two main terms in the final expression. Regarding the first term, through the Parseval's relation, it is easy to prove that there is no frequency overlap among the components of the first term. Therefore, the first term is zero. The second term includes the time average autocorrelation function of the message signal, as given in the final expression. By taking the Fourier transform of the autocorrelation function, we have just derived the power spectral density of the modulated signal is found. Then the total power is calculated by setting the parameter tau in the autocorrelation function to be zero. In the example, the message signal is given as a sinusoidal. The question is, determine the power spectral density of the modulated signal, the power in the modulated signal, and the power in each of the sidebands. The autocorrelation function of the message signal is first derived. Then, taking the Fourier transform of the message autocorrelation function, the corresponding power spectral density is given. Let us now apply the formula we have just derived to reach the power spectral density of the modulated signal. Here, it is important to note that there is no carrier component, since they are suppressed by the modulation. The integral of the power spectral density from minus infinity to plus infinity gives us the power content of the modulated signal. Finally, due to the symmetry of the spectrum, the power in each sideband is calculated as the half of the total power. By this slide, we start discussing the demodulation. In the absence of noise and with the assumption of an ideal channel, the received signal R of t is equal to the modulated signal. The demodulation process includes two steps. In the first step, the received signal R of t is multiplied by a locally generated sinusoid. Notice that this sinusoid has its own phase term rather than the carrier phase. In the second step, the resulting signal is passed through an ideal low-pass filter with the bandwidth W. Let us detail the demodulation steps. In the first step, by the multiplication of the received signal with the locally generated sinusoid, the following signal is obtained. In the second step, by the filtering, the double frequency component is eliminated. In the resulting signal, we can obtain the message signal and the sinusoidal term as a function of phase difference. Depending on this phase difference, we can identify two cases. In the first case, the carrier phase is not equal to the phase of the locally generated sinusoid, and so the amplitude of the desired message signal is reduced as a function of phase difference. In the second case, the phase difference is equal to pi over 2, and so the desired message signal completely vanishes. Based on these cases, it is easy to see that there is a need for phase coherent or synchronous demodulator to make the phase terms equal. Two main methods for the phase coherent demodulation are introduced here. In the first method, a carrier component is added into the transmitted signal. Notice that the transmitted signal is still double sideband, but it is no longer a suppressed carrier signal. Such an added carrier component is called as pilot tone. At the receiver, a narrowband filter is employed to filter out the pilot signal component, and its output is used to multiply the received signal. The second method is based on phase-locked loop, which will be discussed later. By this slide, we start discussing the next method, namely conventional amplitude modulation. The modulated signal for the conventional AM is given here. As you notice, apart from the double sideband suppressed carrier method, the modulated signal in the conventional AM has a large carrier component. The conventional AM does not need any phase coherent demodulation, since it can recover the message signal from the envelope of the modulated signal. However, this imposes some requirements to be satisfied by the modulated signal. Suppose that a message signal m of t is given. If the absolute value of the message signal is less than 1, the message signal follows the envelope of the modulated signal. On the other hand, if this condition is not satisfied, the message signal cannot completely follow the envelope. This results in a distortion. In practice, m of t is normalized so that its magnitude is always less than unity. M sub n of t denotes the normalized message signal. Then the modulated signal is introduced, where the scale factor A is called the modulation index. Similar to the double sideband suppressed carrier AM, in order to calculate the bandwidth requirement, it is sufficient to take the Fourier transform of the modulated signal. As you realize, it occupies a bandwidth 2 times larger than the bandwidth of the message signal. In the example, the normalized message signal is assumed to be a sinusoidal signal. The question is, determine the double sideband AM signal, its upper and lower sidebands, and its spectrum. By substituting the normalized signal, the modulated signal is written. Then its lower sideband and upper sideband can be identified. In the frequency domain, it is easier to follow the lower sideband and the upper sideband of the modulated signal. Note that there are also 2 large carrier components, apart from the double sideband suppressed carrier modulation. Here, the power content of the signal is investigated. Let us first remember the modulated signal and its power content in the double sideband suppressed carrier modulation. It is very similar to the modulated signal of the conventional AM. Hence, if we derive the power for the signal, we can find the power content of the conventional AM signal. This power is calculated here. For this calculation, the average of m sub n of t is assumed to be 0, and so the second term in the integration becomes 0. Finally, the power of the modulated signal is given. Based on the power expression just derived, the following conclusions are provided. The first component is due to the existence of the carrier, and this component does not carry any information. The second component is the information carrying component. However, it is much smaller than the first component, since the message signal is normalized. This shows that the conventional AM is far less power efficient compared to the double sideband suppressed carrier AM. The advantage of conventional AM is that it is easily demodulated through the envelope detection. In the conventional AM, the demodulation is accomplished by the envelope detector circuit, including a diode, a capacitor, and a resistor. It gives an approximation for the original message signal at its output. During the positive half cycle of the carrier, the capacitor charges up to the peak value of the input signal, and it discharges whenever the input starts decreasing. It again starts charging whenever its remaining voltage is less than the input voltage. As you realize, no phase and frequency estimation are required. Then it is a practical choice for AM radio broadcasting. For the proper operation, the time constant of the RC circuit in the envelope detector should be carefully selected. If the time constant RC is too large, the discharge of the capacitor takes too much time. Then the output will not be able to follow the envelope. If RC is too small, then the output of the filter falls very rapidly and will not be able to follow the envelope. For good performance, the boundaries of the time constant can be given. This is the last slide of the part 1.